And welcome back. Thanks a lot for joining us again here at the Glenn Gerberg Weather and Climate Summit. I'm Dave Jones, the CEO of Storm Center Communications, and we're here at Breckenridge, Colorado. We have this question and answer period, and then tomorrow morning is our final session. But we'd like to get right to the question and answer period because we know some of you had questions online, and that's what this piece is designed for. So we have Dr. Jennifer Francis with us from Rutgers University. Jennifer was our first presenter this morning, and we also have Dr. Ben Preston from DOE's Oak Ridge National Lab, and both fascinating presentations. So I think we're going to kick it off with Cheryl Nelson from Storm Center, and she's been monitoring the online questions. So Cheryl?
People here. They have some questions for Dr. Francis, and I've said, hang on, we'll get to you, so thanks for hanging in there. This first question, Dr. Francis, comes from George from Buffalo, New York. And George asks, when and how will waves become shorter to get back to a transient weather pattern versus the long waves where weather is more persistent?
I'm not sure that I can say that that's going to happen. You know, there will be years when we'll see more of the patterns with shorter waves, and then there'll be years when we'll see, you know, more of these very amplified patterns with large waves and persistent conditions. So, you know, as long as we keep pumping greenhouse gases into the atmosphere and we have no expectation that the Arctic won't keep warming faster than everywhere else, I mean, there's no reason to think that we're going to return to perhaps what we consider to be a more normal situation.
Okay, thank you. And I also want to get to Craig from Canada's question. He's also been waiting a long time. Mm-hmm. And Dr. Francis, Craig says, what do you say to those people who say there has not been any climate change? Some regions have changed more than others. What would you say to the naysayers?
Well, I'd agree with the second part of that, that some places have changed more than others. That's clearly the case in the Arctic. It's clearly the case in the peninsula of Antarctica. It's clearly the case in the upper levels of the tropical atmosphere. And that's totally expected. I mean, the climate models have been telling us this for decades now. So that comes as no surprise whatsoever. To say that there's no evidence of climate change, I think you'd have to basically isolate yourself from all evidence that has come out of the scientific community for the last 50 years. You know, there's plenty of evidence, and it is mostly consistent with what we've expected to see happen as we continue to increase the amount of carbon dioxide and other greenhouse gases in the atmosphere. So I just don't think it's a reasonable statement to make in the face of all that we know.
Okay, and Dr. Francis, you again. This comes from Capital Climate, and they say, have there been any studies regarding effects of jet stream changes on latitude and intensity of nor'easter development?
I can't say that I know of one. I mean, we definitely are seeing shifts in latitude of the jet stream in different places, different times of year. So, you know, the logical connecting the dots there would be that in years where the jet stream's farther south, for example, or perhaps, you know, if there's a trough somewhere over North America, if it's shifted east or west a little bit, that's of course going to affect the storm tracks. And there have been quite a few studies about, you know, storm tracks in general around the northern hemisphere and southern hemisphere too. And I would say that there's still quite a bit of uncertainty in terms of trends in storm tracks, whether they're, you know, have definite tendencies to be located one place or another. I think that's still a very hot research topic. Sorry, I can't be a little more conclusive about that.
Hey, we appreciate anything you can give us. Thank you.
Jennifer? My question's for Dr. Preston. I was really interested to see TVA involved in some of the climate adaptation. Probably about half of my area, some of my area, receives their energy from TVA, and I really like hearing that because in the local 6 area, you're also talking about a big coal community, and so you've got a lot of battles when it comes to climate change, even talking about it, let alone adapting to it. So can you expand a little bit on how TVA is doing that for the consumers that may be watching?
Yeah, that's a great question. And what I can't say is to what extent is TVA representative of every other utility out there. But I think one of the, first and foremost, I know one of the things that TVA has been fairly active in is doing work to assess sort of vulnerability and risks of sort of longer term climate change to its operations, to its assets. And that's been done sort of independently on its own initiative. And then also, TVA is essentially, it's one of the sort of publicly owned utilities in the country. So under one of the Obama administration's executive orders, they're required to do a sort of adaptation plan and sort of identify what their vulnerabilities are and what what steps they're taking to sort of anticipate future climate change. So I think they're sort of in that mode of sort of monitoring the risks, sort of collecting evidence, trying to determine where their points of vulnerability are, where's there robust information around what's going to happen into the future that they can take on board. But I think the other thing to remember, and what I've found from my experience in talking to TVA as well as other utilities, is that they operate fairly conservatively. It's very critical that they think about uncertainties and manage risk in an effective way, because you can't really be in a position of, oh, sorry, we're not generating power today, right? Particularly in a system that large. So I think there's sort of this constant evaluation and learning from experience in terms of how do we manage our system in ways to cope with extreme events that they've experienced in the past, particularly drought events and changes in flow regimes, and how do they make sure that they can continue to provide reliability across their service area going into the future. So as I said in my talk, I haven't necessarily seen specific examples where TVA is, say, incorporating a model projection of future climate change in 2100 into their integrated resource planning or making explicit decisions in that context. But I think they certainly pay attention to both what's happening in the climate system, what it means for them, and trying to incorporate that as another factor in their risk management.
Can I ask a follow-up? Is that okay?
Yeah.
Also, I like your urban climate adaptation, the CAT, the tool there for Knoxville. Just on a smaller scale, how might we use stormwater differently than the uses that we're using now as we move forward?
Yeah, well, I mean, that's what we do with stormwater is one of these classic issues in sort of urban management. And the traditional approach has been get rid of it, as quickly as possible and get it downstream. I think in other cities we're starting to think more flexibly about what can we do with that resource. So in Australia, for example, and in other arid regions, rainfall is an important water source. So rainwater harvesting and therefore stormwater harvesting can be an important part of augmenting the water supply in urban areas. If not for drinking water, then certainly for things like irrigation water to keep lawns green and pretty and all that, which is a big use of water in many urban areas. I think people are interested in how we can use stormwater to, and again for irrigation, to say for greening our cities, to improve air quality and augment, urban heat islands. But I think there's also these sort of more out there things in terms of how can we use stormwater in terms of water storage and energy storage within buildings. How can we use water that's falling on buildings and that are 10 stories up and currently draining down and running off? There's some energy involved in that movement of water. So can we tap into that? So issues that aren't ideas that aren't ready for prime time, but certainly there's a lot of thinking about water's an increasingly precious commodity. So how can we use it in flexible ways?
Do you look to TVA? Because we see the visual of it driving over Barkley and Kentucky Dam. And so that's that's in the bigger sense using stormwater for energy.
For energy production. Right?
And so I guess it's kind of like really bringing it down to the micro level for a business, say.
Right, right. And it's not just stormwater, so wastewater of all types. So, one of the things that some utilities are looking at in terms of cooling water for power plants is, well, do we have to pull water directly out of the river system, or can we reclaim water from runoff or wastewater treatment systems and use that as a source for cooling water? So this interface between energy water, the energy water nexus, is sort of this hot topic. Certainly for Department of Energy, it's a big area for us in terms of where we're going with our research and development, but certainly across other agencies and universities as well.
Thank you.
Yep, sure.
Okay, I have a question for Ben. Many people think that burying power lines is the pathway to resilience and resilient communities. And I'm just wondering, what kind of cost benefit is there to bury power lines? And I guess they have to come above ground at some point. So what have your studies said about that?
Yeah, I mean, we haven't studied that specifically, but I've certainly, that's an important topic whenever you talk about grid resilience. It's like, well, we know we get ice storms, we get wind events that knocks down trees and limbs, they fall on the power lines, and that causes havoc across the distribution system. So one of the most common types of electricity outages that we see. And so the natural response is, well, bury the power lines, because we see that happening in densely populated areas, and certainly in European cities we see that a lot. But often the cost-benefit analysis, around that isn't great. And there's a number of issues that arise. So one, it costs a lot more money to put a line underground. And so to recoup that cost, that means you have to be anticipating a fairly frequent disruption to above ground power lines. So that's sort of one issue that comes into play, and the other is accessibility. So yes, you'd expect buried power lines to not be disrupted as often, but then when they are disrupted, it takes a lot more effort and energy to get out there, find the fault, dig it up, fix it, and rebury the line.
Gotcha.
And then, as you pointed out, they have to come up somewhere, right? So I know people that, bury the lines from the telephone pole to their house to make themselves more resilient, but if your neighbor hasn't done the same thing, then, is there any real benefit from that? So it seems like a no-brainer that we should be burying power lines, but, in terms of the return on investment of that, it's not great. And so you just have to simply, if you're committed to maximizing resilience and you have a very low tolerance for failure, then you might choose to make that investment, but many choose not to.
That sounds great. And another question was, the computing power that you have there at Oak Ridge is impressive. And as you get to modeling climate, perhaps down to 10 kilometers, I'm just wondering, with Noah and here, with Lance Rothfuss at NSSL, could that be a valuable input from a 10-kilometer climate model to what kind of climate services NOAA might be providing in the future? And I'll hand the microphone over to Lance if he wants to answer as well. But I'm just wondering if you have worked with NOAA at all in trying to head towards that goal of using your outputs as inputs for their perhaps decision making.
Yeah, it's a great question, and it makes a lot of sense. I think the challenge is sort of the timescale issue of what NOAA might be interested in versus what DOE might be interested in terms of their climate modeling, and that's why you have sort of different capabilities and different research questions across different agencies. But I think to some extent we have done ourselves a disservice by having this disparity between weather and climate. And really what you'd like to be able to do is eliminate that disparity and be able to have sort of capabilities that can fill those temporal gaps and move across a range of temporal scales from what's happening in the next hour and the next day all the way up to what's happening in the next decade or the next century. And I think as we push our Earth system models to these sort of spatial and temporal resolutions that are similar to what we're seeing from, say, global weather forecast model, I think that creates new challenges, and it's no longer sort of the excuse of, well, we're modeling the climate, not weather. I think that excuse is going to break. You're not going to be able to use that excuse anymore, and we might see some convergence, both in terms of the models that people are using, as well as the types of computational resources that people are using to do their modeling.
This is Lance Rothfuss, National Severe Storms Laboratory. Actually, I'll follow up a little bit because you set me up for this, and then I'll ask a question too. I think there is that interface between the climate down to the weather sort of thing that NOAA and your laboratory can and should be working on. I think we already have in some cases. I look at it more from the weather side, obviously, for Severe Storms Laboratory, and the impact that certain storms will have on infrastructure and these kind of things that can be modeled and can be tested. And I would love to see that happen more on a regular basis, such that you do that over and over again, then you start to develop a climatology of impact, right? So I think there are places there that we need to spend more energy and effort looking into. My question is sort of a broader question of vulnerability of the infrastructure, the power grids and such. I think from what I heard in your presentation that there is one phenomenon that is probably the most impactful to the entire infrastructure, power structure, and that would probably be drought and the impact. But would you say it's something different than that, or is there one type of phenomenon we are most vulnerable to? Only reason I say drought is because it's sort of a long-standing thing and can really pile up a problem, whereas hurricane is there, it's gone, and you rebuild and move on. So do you have one phenomenon that you're most worried about?
No, I don't. I mean, I think, so drought's an interesting one because, particularly for places like the southwestern United States, that's where we see the most convergence among different climate models, that we're going to have reductions in at least annual rainfall. Granted, it's sort of an arid environment in general, but if we have reductions in snowpack and therefore reductions in flow down to Colorado, then that has a big impact on hydropower as well as other downstream uses of water resources. And particularly that becomes a sort of persistent state, and we have developed an energy generation infrastructure that's built upon and designed for a climate state that no longer exists, then that can be a game changer and a transformational change in the energy system. But I hesitate to say that there's sort of one key impact, because it really depends upon scales and sort of who's being considered, right? So if you're a homeowner and an ice storm or a hurricane knocks out power for a week, for you, that's a pretty big issue, and you're not really concerned about what's happening with drought in another part of the country. The other issue is some of these things that affect generation capacity. So say hydropower or cooling water for electricity generation. So say you're having to derate your power plant because of chronic sort of water quality or quantity problems. Okay, but we have a grid, right? So we're able to compensate and do on a routine basis for reductions in electricity generation in one place with surpluses in another place, and the utilities have to have a certain amount of excess capacity in their systems anyway. So I think what we should be thinking about. So for me, what I'm interested in is one, the sort of regional distribution of issues, because I don't think there's necessarily a national problem across any of these types of hazards. There are significant localized problems, and so figuring out what those are in each market and location is an important one. And second is figuring out what are those game changers, right? So if you have a power plant that can no longer discharge cooling water into a receiving body because the ambient temperature of the water exceeds EPA's regulatory threshold, and that becomes an idle or stranded asset, for that particular utility and that piece of infrastructure, that's a fairly substantial issue. And there's probably other examples across the energy system where you hit these thresholds where you have to just really rethink what you're doing at different scales.
This is Tim Brown, Desert Research Institute, Reno, Nevada. This is for Jennifer. The PDO that you talked about in your presentation this morning, do you think that's its own thing, or is it related? How it might be connected to the tropical Pacific, influence? Any thoughts on that?
Well, I'm not a PDO expert. I know somebody who is. Went to school with him, Nate Mantua. Just looking back over the record that we have, which doesn't go back all that long when you talk about something that fluctuates every 10 years, it seems to be not showing any signs of a trend. So I think just based on what we have to work with right now, there's no indication that it's going to, tend towards its, one phase over another with any regularity. So I'm not aware of any connection at this point.
Okay, thank you.
I have a question for Ben.
Go for it.
Is that okay? So you showed that matrix of model simulations for, I think it was a few decades in the future for freshwater resources or something like that. And you said that the models are so different in their simulations of that time period that it's not of much use to the decision makers that really need to get that information. But potentially it's not the mean state of the future that we care about as much as the variability of the future. Yep. So I'm wondering if you have a similar matrix like that for those different models simulating the extremes, and whether there's maybe better agreement in terms of the extremes rather than the mean fields.
Yeah, that's a great question, because that's the challenge I think we run into on the modeling side is, we think we know what information stakeholders want and what matters, and it turns out that there's probably stakeholders out there that, they're not interested in what's going to happen with the mean, but the extremes become important. And yeah, in the sense of rainfall, I'm pretty sure that if you're looking at extreme rainfall events among different models, at least in terms of the sign, you would see much more consistent results and convergent results. So this idea that you have this accelerated hydrological cycle, and there's water vapor feedbacks, and therefore more extreme rainfall events or of greater magnitude, I think that's a more robust conclusion that you can take away from the models. And if that's the endpoint you're interested in, then that's probably useful information. So thanks. It's a very important point. And and if you're talking about temperature, then it's a much easier story, and all the models are much more convergent, both in terms of average temperatures, but also temperature extremes going up. So it all comes down to how you use model results. Use them in ways that are effective to and useful for your stakeholder. And so I think the concern we have is that someone will look at that type of matrix and say, oh, you're all over the map, there's nothing useful here, so they ignore it. But you might be able to say, well, if we're looking at a different variable or different type of output, or if we look at, say, the predominance of the models, then there's a different story that you can tell where you actually start getting into some useful, robust conclusions. And then what people are doing in terms of arguing about not all models are created equally, and therefore, if you look at a subset of models that seem to do particularly well in their representation of a historical climate, they tend to be more convergent, and therefore you can have more confidence in those results. So it's a very good point. Thanks for that.
I have one more question. Lance Rothfuss, NSSL. And I was going to ask this question last night at the town hall, but there's so many other good questions I didn't get to ask Dr. Francis this. In your presentation and a couple of other ones, it was almost a foregone conclusion that the carbon dioxide is increasing. All right, and since the naysayers thing has come up already online, I heard a while back what I thought was a pretty good explanation, because some of the naysaying is about, well, millions of years ago the carbon dioxide level was high back then too. So how can you prove that it is man-made? And I think I heard the answer is in the isotopes itself, understanding the isotopes, but we don't really communicate that out very well as to why it's different now than it was back then. So is there a succinct way we can communicate the isotopes as being the insight as to why it's different now than it was back then? Or is there some other way to say that?
Just in terms of the carbon dioxide itself, it's, crystal clear through the isotopic analysis that the fossil fuels burning is the source of the big uptick in carbon dioxide in the atmosphere that we see now. In fact, before the beginning of the 20th century, we were actually on a cooling trend, and this was consistent with shifts in the Earth's orbit and shifts in the Earth's tilt, which is what caused the climate cycles of the past. So we understand why the climate changed before. We know that the carbon dioxide responds to temperature changes that were forced by orbital changes, as you thaw permafrost and so forth. As the oceans warm up, then carbon dioxide is released into the atmosphere, so that couples those two variables in the past. But they're very uncoupled now in a way, because the carbon dioxide is now leading the temperature. The Earth can't change fast enough to keep up with the increase in the carbon dioxide. But the carbon dioxide is, it's just clear as a bell where that carbon dioxide is coming from, and there's really no other explanation for where it could be coming from.
Right, and I think we all get that. I guess what I'm saying is we miss the opportunity to explain the isotopes as being the red flag as to why this is different. And just for the broadcast community here especially, to bring that out as often as possible. I haven't heard it as much as I thought I should in the argument of that.
Well, just to comment on that, I think part of the reason why that doesn't enter the sort of public discourse on this is it's not an easy explanation. Because if you went out and asked the public how many people know what an isotope is, much less different isotopes of carbon dioxide and what that means and how you measure them, it's a hard sell.
I tend to describe it as different flavors of carbon dioxide, and it seemed to work
very good,
when
very
I did
good.
that.
That sounds great, Lance. Thanks so much for that question. And it's been a terrific session here. This is one of the longer ones for both questions in-house here and online. So we really appreciate you taking the time and also being patient online for asking your questions. That's going to do it for today, but for tomorrow morning we have another session starting up, and it's going to start with Greg Mant from NOAA. He is the program manager for the GOES-R satellite, R, S, and T, and the GOES-R series of satellites, which are really going to revolutionize the way weather is forecast, the way the Earth is observed, the way the sun is observed. So please stay tuned and tune in tomorrow morning for Greg's presentation. Always a lot of eye candy Greg has because of the visual nature of the GOES-R satellite. So, and then after Greg presents, then Michael Ventris from WSI will talk about atmospheric drivers for the winter that we're experiencing right now, and how those drivers may move into other seasons. So it's going to be certainly an exciting morning. We hope you join us back, and then we will ask you on the internet audience to ask your questions during both of those sessions, because we have to pack up right at noon tomorrow to see if any of us could possibly get anywhere near the East Coast. So thanks again for watching, and that'll do it for today from Breckenridge, Colorado. This is Dave Jones with the Glenn Gerberg Weather and Climate Summit. See you tomorrow morning.